Thank you for the presentation. Yeah, so as I've said, the name of the title of the paper is Evaluation of Updating Strategies of Conformal Predictive Systems in Presence of Extreme Events. And this is worked on together with supervisors Lars Karlsson, Ernst Alberg, and Henrik Boström. Let's see. So the outline of this talk is as follows. There will be a brief introduction and some motivation to the work, and then look into the methods, and then the empirical study that is considered, and then to follow is some concluding remarks. Let's begin with the introduction and some motivation. So, working at Stena, which is a shipping company, which transports both freight and passengers. As one might expect, planning is of importance when it comes to reducing costs and increasing margins. For example, planning the number of crew needed on a specific sailing. If you have a certain amount of passengers, you need a certain amount of crew in the case of emergency. And traveling with too much crew is expensive, and calling crew at the last minute is also expensive. So the earlier you can plan, the better. And the same thing goes with a lot of things such as food and whatnot. And one way of doing this, apart from just your gut feeling, is using some statistical modeling, or even better, perhaps some conformal predictive system, which will even give you more information about what might happen, or how many passengers, for example, that you might have on board a sailing in the future. However, what one would want in the case of using some conformal predictive system is validity, and with the risk of some shift in the underlying distribution. For example, in the case of an extreme event such as a pandemic, we might see, or as we saw during 2020, a radical drop in number of passengers as people were restricted and borders closed. So this raises the question: how do we handle these type of events, and how do we handle these kind of changes in the data, and when do we update our models, and how do we what kind of strategy should we employ to detect these changes? So that is some of the questions that led to this paper. So, as I mentioned, conformal predictive systems, and as we've heard in several other talks, it's a system that generates a distribution Q for some test instance X, such that we get the probability of the true label being smaller than or equal to some Y. And in the planning process, this can be, or the decision-making process is useful as we get more information, and we can take out the, or as Henrik showed, the confidence interval which we're interested in, and we can make better decisions, essentially, and make have a specific error rate which we'd want. But as I mentioned, for validity, we need the data to be IID, and in practice, this is not always the case, and especially in the case of some extreme event, such as a pandemic, where everything changes overnight. And for this, so that's why we need some way to handle this and to detect it as well, which we've heard other talks on this topic as well. But in this paper, we use a specific method called the split conformal predictive system, or split conformal predictive distribution, which splits the data into two disjoint sets, a proper training set and a calibration set. So when we observe new samples, we essentially have several choices what we want to do with those samples. For example, we could just add them to the calibration set, or retrain using them in the proper training set, or just disregard them or leave them for later if we want them later, perhaps. So there are several options what we can do with new observations. Furthermore, I mentioned change detection, and something we heard mentioned yesterday was the algorithm simple jumper, which is to test online if the data is independent and identity distributed. So if we use conformal predictive system, we get these p-values, and which should be uniformly distributed. And we can use these and bet against the null hypothesis. And for each observation, we have some capital S, and when this capital grows or exceeds some predetermined threshold, we can consider that, or we can say that some change has occurred in the underlying data, and which can then trigger some update or some action on our model or on our system. So what we have done is we have designed 6 strategies, 6 ways of updating our model, or as the first strategy says, no update, which is essentially a benchmark where you use your historical data and you generate this initial split conformal predictive system, and it's kept unchanged, and all the new samples are discarded. And as one would expect, if there's any change in the data, there's no chance to adapt. The second strategy is using a sliding window for the calibration set. So we want the calibration set at least to be ID to the new observations and the new test instances. So if we every F test observation, or in this case we use 7, which would correspond to a weekly update, we update so that the calibration set consists of the L latest observations. So it's always the most recent observations in the calibration set. However, the underlying model is the regression model is kept unchanged. Then moving on, we have strategy 3 and 4, which becomes a little bit more complex, or computationally at least, where we, in strategy 3, create a completely new system. So we retrain, we use all the previous data, all the data that we've seen, and we create a completely new SVS, and where the data points are split randomly into the proper training set and the calibration set. Strategy 4 is pretty much the same as strategy 3. However, we throw away the oldest samples. So we only use the L most, where L is different from in strategy 3 here. But we use only use the latest samples, both for the calibration set and the proper training set. And then finally, we have strategy 5 and 6, where we introduce some this change detection, where we use this sleepy jumper to detect some change in the data. And when we have detected some change in strategy 5, we update the calibration set with the largest number of most recent samples where a change is not detected. So we go backwards, essentially, looking at when we can detect a change going backwards. And this is set to the new calibration set. In strategy 6, which is also similar to strategy 5, we do the same thing. So we only update when a change is detected. And we also use the most recent, or the largest, most recent samples where a change is not detected for the calibration set, and we update the model with all previous data or all the data before that point. I hope that is fairly clear. All right, so when we have these methods and we're using state conformal predictive systems, we want some kind of way of evaluating which method performs the best. And the first thing that might come to mind, and which we have seen in previous talks as well, is using CRPS, where we're comparing our generated distribution to the oracle, which would be a step function at the label. However, this does not fully capture if the model is, or if we're getting valid predictions or valid distributions. So we might have some shift in the distribution. However, I mean, we could have a step function right next to it for all predictions or all distributions, but so you might get really low CRPS, but the actual probabilities would be way off, perhaps. So one way of tackling that part is to look at the calibration plots. So which is, for those who are not familiar, is if you look at the theoretical coverage. So if you look at, for example, 0.7 around here, we'd expect to have 0.7 coverage in our distributions as well. To have seen 70% of the label should actually be smaller, whatever value is given by 0.7. However, in this fictive example, we see that the coverage is lower. So there's a deviation from what we expect, which is this dashed line, or in long term at least. We want the red curve, which is our observed coverage, to align with the dashed line. However, we have this yellow area, which is some deviation, and we can measure this essentially, and we take the LT norm of some discrete points and measure the deviation. And this way we get actually a measurement of how far away is it from being valid. Essentially, we can compare the different strategies. All right, so on to the study and what we've actually looked at here. And as I mentioned, a pandemic hit. So this is some data from a route which standard sales. So this is from 2017 all the way up to the end of 2020. And around here is where the pandemic hit, and we see this. Well, first of all, we see the seasonal trend here, and then or behavior, and then we have a serious drop in volume this last year. So we were first of all interested in how what happens if we use our system and use our predictions, and then this hits. What strategy should we use? But also, coming out of this pandemic, what kind of strategy should we use to get the best predictions, to get the most valid results, and to simulate this without actually generating any data, we simply moved the data from 2017 and relabeled it as 2021 in this fashion on the right here. So this would simulate that the passenger volumes would go back to normal essentially overnight. However, this might not be very realistic, but it still captures a interesting event that this drop and then everything coming back to normal, and how do we actually handle these situations in this context with these methods. So furthermore, the data includes some features in the weekday, month, weekend. So if it's a weekend, yes or no. Week number, 1 through 52, and then what we call the booking state, which is 2 weeks before the departure, the number of bookings on that sailing, on that departure, and the number of guests that these bookings include. So as you can imagine, there's quite a strong correlation between number of bookings, guests, and the actual number of guests at the departure, which is the target which we want to predict to do our planning. And then, so we went about this by first creating a SPS using the data from 2018, 2019. So that would be, these 2 years. I hope you can see my mouse here. So these 2 first peaks here, essentially, right before the drop in volume, to initialize the system as everything was normal, and then evaluate it on the 2 following years. So we call this year 1 and year 2. So 2020 is year 1 and 2021 is year 2. So we run the strategy after training it on 2018 and 2019. We run it on and evaluate it on 2020 and 2021. And we also do this with and without the booking state. And we repeat everything 10 times, as there's some randomness in the underlying model. We use a random forest here. And then we compute the average CRPS and the calibration plot for all the 10 runs for each strategy. So when it comes to evaluating, it's not crystal clear with which method one should use, and as we've talked about earlier, it might depend on the application and how one actually goes about and uses the output from these systems. But if we start by just looking at the CRPS, we first observe that with the booking state, we get much better results compared to not having the booking state included. And furthermore, we see that so strategy 3 here is where we create a completely new system every 7th observation. And I mean, the strategy 6 here, which does way fewer updates, is competitive with the strategy that updates regularly. And that's also the case when we look at CRPS without the booking state. So that's in and of itself is interesting and quite nice, because that means we don't have to do as many updates. We can only update as soon as we detect something, essentially. So year 1 and year 2. So this is not addition, but it's all the data combined. Just to clarify that. Moving on to the calibration plots and the LT norms. The results don't really transfer here. So here we don't necessarily see that strategy 3 is the best. Rather, strategy 4 would be perhaps better, which is also interesting that the best CRPS doesn't reflect the best or the most valid results or valid predictions. So that is also interesting when it comes to the application. What is one looking for, and how do you determine what is important? And as another thing which you might notice is year 1 and year 2 looks in many cases much lower than year 1 and year 2 separately. And the reason for example, S4 here or S2 as well. And the reason for this is that in year 1, we had a drop in volume, so we essentially over predict how many passengers we would have, and thus getting these biased estimates. And in year 2, the same thing happens, but we have more passengers. So and in combination, they essentially cancel each other out, and everything looks great. So if you just look at all the data combined, we'd have this red line, and everything would be perfect. However, looking at them separately, we see that is not the case, and this goes for most of the methods shown above. All right, and finally, some concluding remarks. Well, it appears that, and as one would expect, updating with the most recent data is good. However, updating when a change is detected is definitely competitive. And as I said, the best strategy may depend on the application and also even the data set used here. So yeah, there's definitely some future work that can be done here, and especially looking at bigger data sets or other data sets, and include other types of changes, so not just these dramatic changes, but perhaps some gradual changes, see what happens and how one could handle those. And with that comes also perhaps developing more complex strategies, and as also mentioned, evaluating from the user's perspective, what would the actual profit be from one strategy compared to another. All right, I think that's all for me. So thank you for your attention, and thank you for listening.